Okay, so what today we're going to do is we're going to do a third method of finding enthalpy. Okay, so you can find enthalpy using calorimeter, where you basically find the heat, then find the moles, take the heat divided by the moles, right? Then you did it using Hess's law, where there's different reactions that if you add them up can give you the reactions that you want. Today we're going to use another method called the standard enthalpy of formation. Okay, and the standard enthalpy of formation is it's the energy needed to form a compound, basically, right? Just like if I give you a bunch of Legos and I want to go, hey, I want you guys to build this house for me. How much energy did you put in to build that house? Then let's go with a car. How much you put energy to make that car, right? So the energy you put into making those things is its enthalpy of formation. That's how much energy you use to form it, basically, okay? Now, if you look at down here at the bottom where it says using the standard heat of formation, notice the first one, that is CO. Okay, so carbon monoxide, to form carbon monoxide, so to take carbon and oxygen and to form it, you have to release 110.5 kilojoules per mole of energy. Okay, so carbon has a certain amount of energy it has, oxygen has a certain amount of energy, and when you put it together, they actually have lower energy than they start before, and so they release that energy. So this process is exothermic, right? Notice CO2, very similar, but look how much more energy it gives off. It gives off minus, or exothermic, 393.51 kilojoules per mole. Make sense? So every compound has an energy of formation. Every compound has a certain amount of energy that is needed to create it, right? And that energy could be put in to create it, or it could be released after you created it. Does that make sense? Okay. So anything that's positive means, again, you're putting in energy to create that compound. Anything you take away, negative, would be an exothermic to give off. Notice, though, there's this guy right here. See that? That's C small o. Is that carbon monoxide? No, that's cobalt, isn't it? Cobalt, as we know, is an element. Does it take any energy to form an element? No, it's there, right? It's like when I start with a piece of Lego, was it any energy to form a Lego? In your case, no. But yeah, there's energy to form a Lego, but we don't care because you start with the Lego, right? So because it is an element, its energy of formation is always 0. So you do not have energy of formation for elements, okay? So element just formed. Now, the good news is all the energy of formation will be given to you in a list just like this. Okay, so you don't have to memorize it, you don't have to write it down. It will all be given to you, kind of like Hess's law. All the formulas, the equations will be given to you. So all you have to do is this. So to solve for energy of formation, so this is going to be enthalpy based on energy of formation, right? So this is enthalpy using energy of formation, or sometimes you will hear it as the enthalpy of formation, enthalpy of formation, and you will see it as delta H with a little f right there. Okay, and that little f, like I heard earlier, it's not Fahrenheit, it is formation. It forms something. Okay, this is how much energy used to form that compound. Okay, so enthalpy of formation is the energy exchange, either positive or negative, during the formation of a compound. Okay, so that's the definition of energy of formation. Okay, that's the definition of energy formation. Is the energy exchange during a formation of a compound. Okay, so to solve for that, you're going to find the delta H of the system, which is basically the whole thing. Okay, what you're going to do is basically it's going to be the sum of the product. The sum of the delta H of formation of the product minus the sum delta H formation of the reactants. Okay, the products and the reactants. Meaning what? Meaning we just have to sum up all the energy of formation for the reactants, and we subtract that from all the energy of formation from the product. Okay? Now, in the whole equation, it looks like this. Delta H of the system, or the reaction actually. So not the system, sorry, let's write this as reaction. So this should be Rxn. Okay? So it's Rxn for reaction. It's equal to sigma, which is the sum of the coefficient multiplied the delta H of formation of the reactants. Okay, reactants minus the sum, the coefficient multiply the delta H of formation of the reactants. Sorry, the other one should be product. Reactant. And then this one over here should be product, not reactant. Sorry. Products. Okay. So both equation is the same thing. Sigma, which is this E right here, all that means it's the sum of. Okay. So the difference between the two is that coefficient. That coefficient is going to be important because that coefficient tells you how many of those molecules you need to use. Okay? So how many of those molecules you need to use. So if we go back to the equation, okay, so let's go back to the equation here. In this equation right here, you notice you have each one is just one of them, correct? So the first thing I would do is I would write the enthalpy of formation for each one of those. So I want to start with this one right here. The cobalt. What is the energy formation of the cobalt? 0. So I'm going to put a 0 on top. Then I'm going to go to the next one. CO2. What's the energy formation of CO2? Negative 393.51, right? Then I just go to the next one. Cobalt oxide. Cobalt oxide is this guy right here. So that's negative 239.3. Then the next one is this guy, which is carbon monoxide, which is going to be negative 1110.5. So far, so good. Now, what was the formula? Product, sum of the product, subtract sum of the reactants, correct? So sum of the product would be this guy, sum of reactants would be this guy. So over here should be 393.51 total. On the other side, we're going to take that 293 and subtract the 110. So that's negative 239.3. Subtract a negative, add that together. Sorry, it's a sum. So you add that to a negative 1110.5 equals. So now this side is negative 349.8. And remember, it's the sum of the product minus the reactants. So basically, which is equal to the delta H of the reaction. So the product would be negative 349.8. Be careful with the negative. Subtract a negative 393.51. So again, remember, a subtraction and a negative will become a positive. So you technically have a positive here. So that's negative 349.8 plus 393.51 equal, and you get 43.71 kilojoules. And since the positive is bigger, it's going to be a positive. And this is the delta H, or the enthalpy of the reaction. This is the same as the answer to calorimetry enthalpy. That's the kilojoules per mole. This is the same answer as the Hess's law after you finish modifying and all that stuff. Okay, make sense? Okay, so if there's a coefficient, then you just have to multiply that substance by that coefficient. Okay, so all you have to do is multiply that substance by that coefficient. All right, so let's take a look at another example. Okay, so if we have this example right here, go ahead and take a moment and let's see if you can do that example.